Guest speaker, Professor Akira Wada, is from Tokyo Institute of Technology. Professor Wada has been with the Tokyo Institute of Technology since 1982 till the March of this year. His research interests are structural engineering of architectures and buildings, seismic designs especially, seismic isolated structures, damage control design, and computer simulation of structures. He is the president of Architectural Institute of Japan, and he becomes a member of Science Council of Japan at this October. CTBUH decided to give him a Fazlur Khan Lifetime Achievement Medal 2011 on November 3rd at Illinois Institute of Technology. Professor's presentation will be on tall buildings in earthquake-prone countries, which is quite meaningful, especially when there was a catastrophe on last March in Japan. Let's welcome Professor Wada with your applause.
Thank you very much, Chairman. It is my very pleasure to present our tall building technology in earthquake-prone country. I'd like to thank you, Professor Sang Dae Kim and Jae-pil Choi, and many friends in Japan. March 11 earthquake and damage I would like to explain to you. Origin time is 2 o'clock 46 minutes. March 11. Magnitude is 9.0. Number of dead and missing approximately 19,000 people. Number of displaced people 75,000 now. And the number of damaged houses approximately 270,000. And the direct money loss is 200 or 300 billion US dollar. This is 1/4 of Japanese annual budget. The earthquake is very big. North and south length is about 500 kilometers, and width is 200 kilometers. There are 3 big earthquakes during 1 or 2 minutes. Okay, after the earthquake, there is no buildings at all. There are many places like this. And the reinforced concrete buildings fell down. And the oil tank is very light. Oil itself is lighter than water. The oil tank is very unstable in the deep sea and very dangerous. Oil will be bound. And big ship also go to the land. Very difficult to bring back on the sea. This is very heavy when there is no water. And the lessons learned from March 11 earthquake, huge tsunami once for 1,000 years, very infrequent how to deal with. And restoration of almost completely damaged towns. There are 500 towns were damaged. And beyond the design scenario, we have to consider the needs to long-term views for public safety assurance and needs more reliable structures for the next big earthquake. Not only earthquake, but also strong wind we have to consider when we want to build very tall buildings in the world. And the left-hand side, peak ground acceleration distribution. Maximum acceleration is 2.7 g. And the maximum peak ground velocity displacement and distribution, maximum is 3 meters per second. And there are many earthquake records in these 20 years. Northridge earthquake 17 years ago, left top. Many tall buildings in Los Angeles were damaged, but this is very small compared to our big earthquake. The bottom is March 11 earthquake. And the Chile earthquake last year is almost same, very large and very long. And the Chichi earthquake, you will know, a 12-story reinforced concrete apartment turned down perfectly. I think you will remember. It's a second earthquake. And there are many earthquakes in these 20 years. And the response spectrum I showed in Sendai, almost this level is once 500 years response. But more than 1 second, not so strong. The less than 1 second period is a little big. So many buildings could survive. If the spectrum over 1 second until 3 or 4 seconds is like a peak of 1 second, I think many buildings would be collapsed. And I'd like to discuss about 3 cities. Sendai is very close to the epicenter. And the next, I would like to discuss about several buildings around Tokyo. And finally, I'd like to show one building in Osaka. From Osaka to epicenter, I think 800 or 1,000 kilometer distance. And this is Sendai city after the earthquake. And I think you cannot see any damage. But we found the permanent displacement apartment building. This is 14-story, not tall building, but residual permanent displacement is a little large. No one want to live in this building after the earthquake. They will demolish this building. I think you cannot understand why, but the permanent displacement, they don't want to live after the earthquake. You can see the damage, not structural member, and there are permanent displacement. And about these 30 years, Japanese contractor and researcher and designer make retrofit to old building. This building was retrofitted before the earthquake, so this is okay, no damage. And there are many braces around the building. This is also retrofitted school building, and no damage. And this building, only first and second story were retrofitted, but the third story, not strengthening by the brace. So damage was happened at the bottom of the column at third story. We need more braces to this building. And there are many problems for the non-structural components. This is a ceiling fell down from the Sendai Shinkansen station, but no one has any damages. This earthquake is very long. They will left from the dangerous ceiling, so it is okay. But more than 1,000 or very many ceilings fell down by the earthquake motion. And this is a gymnasium of the high school. Very dangerous. And furniture was broken. And I would like to explain the behavior of the tall buildings in downtown Tokyo. 35 million people living in Tokyo metropolitan areas, but we will have big earthquake in next 30 years. This is a video in the tall building. This about 40, there are 340s building connecting by the damper. I think you can see the movement of the connection. We have two levels when we design tall buildings and ordinary buildings, level 1 and level 2. Level 1 is the return period about 20 years. And level 2, we consider 500 years return period. And this XYZ response spectrum is between level 1 and level 2. Level 2 is 5 times bigger than level 1. And we expect in design level 2 earthquake. This level 2 is 3 times stronger than March 11 earthquake. And in Shinjuku, there are many tall buildings, but not 800 meter, but about 200 meter high. On the left-hand side, little old building without no dampers. And the second building is more 10 years before left-hand side, but last year, 2 years ago, they add oil dampers. They expected the very long natural period earthquake will come in near future. So this is very successful story. And the right-hand side, 3 years ago, they built the base seismic isolated tall buildings for prep school. This is Kogakuin University, but there is no damper and no seismic isolated. About 30-story building. And left-hand side, the first natural period and mode. Second, right-hand side, second mode and second natural period 0.93 seconds. And from left to right, 400 seconds, but vibration was not stopped. More than 10 minutes, the vibration continuously movement. And there is no artificial damping system. The vibration cannot stop more than 10 minutes. And the second mode vibration is also very large. And the second building, this building is originally designed and construction more than 34 years ago. But the last 2 years ago, they put oil dampers. But this building originally has a passive control system. You can see the floor to floor, two shear walls, but the middle part is no concrete. There are many reinforcement bars, elastoplastic behavior they expect, and this is some kind of damping system. More than 33 years ago design, very new design at that time. But young engineer discuss and studied this behavior of this building and long natural and long period and long duration earthquake. This passing damping system is not enough for big, long earthquake. So they decided to add oil dampers. They add from 15 story to 39 stories. This is very new dampers, very stiff brace and oil damper. I think very simple idea, I think. But during construction, the worker and engineers are staying here. They develop new construction system. They put these devices by post-tension by the rod. And this is a record at the March 11 earthquake. Blue lines is acceleration. About 150 Gauss. Please check the right hand side ground motion centimeter per square second. And the left hand, the red lines displays the displacement of the top of the building. I think the maximum displacement will occur. The acceleration of the base is maximum. All of them will sinking. But maximum displacement has occurred after the maximum acceleration. But when I was young engineer, I stopped the calculation around after the big acceleration. I stopped the analysis. But we cannot recognize the maximum displacement will occur after the maximum acceleration. But on the El Centro or Taft, very old earthquake record has not high fidelity, so we cannot analysis for long natural period using very old acceleration record. Now we have new technologies. We can study these behaviors. And left hand side east and west, right hand side north south. And the earthquake happened March 11 is green. But we consider the black dot line about 2 or 3 times bigger. And the maximum displacement at the top of the building, this building is 55 story, it's more than 50 centimeter, plus minus 50 centimeter. And the total amplitude is more than 1 meter. But we consider 3 times earthquake. If big earthquake like this designed level 2 earthquake come in future, the top of the building will move 1.5 meter, 1.5 meter, total 3 meters. I think they cannot stay in the top of the building. You want to make a tall building more than 100 story or sometimes 200 story. If you make these very high story building in Tokyo, I think they cannot stay at the 800 meter floors. Please don't forget. This is analysis by Taisei Corporation, and their office in this building. The first first 60 seconds, the vibration is almost like to the second mode motion. But finally, this building move first mode. And the maximum displacement when they have not any additional dampers, 20 or 30% more vibration, I think 80 centimeter plus minus. But they add additional damper last year. The maximum displacement is 50 plus minus 50 centimeter. But this is very large. And finally, I'd like to explain the seismic isolated tall buildings. Total natural period is 4.7 seconds, but the story is not, the building height is 134. This is orbit of the basement, plus minus 80 millimeter, not so large, but structure's interstory displacement is less than 1 over 1,000. Very good performance they can get. The bottom is acceleration at the ground, but for top 3 acceleration record is inside of the building. The acceleration in the building is smaller than the ground motion. If there is no seismic isolation system, the vibration of the superstructure is bigger than the ground motion. And this is not so tall building, but very good performance. It's recorded. This is a design by Takenaka Corporation. They measure many acceleration in not only the superstructure but also basement and 50-meter deep in the soil. There is seismic isolated layer, the very effective system you can understand. The acceleration in the building is about 60 Gauss, but ground acceleration is more than 150. And finally, I would like to show the tall buildings in Osaka, about 500 kilometers west from Tokyo. The maximum displacement at the top floor is 137 centimeter. I think you cannot believe. 500 kilometer west. This is 800 kilometer from epicenter. But the top of the displacement at the top is more than 1 meter. Plus minus 137 centimeter. This is very serious problem now. They are studying how to reduce this displacement. And the passive control structures, not only the dampers, but also seismic isolation. There are more than, I think, 3,000 or 4,000 buildings has already seismic isolated or passive controlled. And we measured many records, and we have to understanding true capacity of the structure for preparation against a stronger shake that will be definitely happen in these 20 or 30 years. And just before I came here, I climbed up the Tokyo Sky Tree The total height is 634 meters. I took the photo at from 475 meters high. We want to make, this is a TV tower, but we would like to make more than taller than 300 or 1 kilometer building in Tokyo, like your project. And we appreciate much for your sympathy and support for March 11 earthquake in Japan. Thank you very much.